behind this speaker. Okay, better.
Yeah. So Professor Datta is a fellow of IEEE and the distinguished lecturer in the IEEE Electronic Device Society with a number of awards. So today he's going to tell us about the emerging devices beyond CMOS. Let's welcome up.
Thank you very much. First of all, I'd like to thank the organizers of this workshop for extending this kind invitation for me to come and speak about some of our work here in Hong Kong. So far, it has been a very exciting workshop. And it was great to meet some old friends around here, familiar faces. So the title of my talk is Emerging Devices Beyond Silicon CMOS. We already, Silicon CMOS is well on its way and will be the mainstream technology for even in the near future, but there are some exciting developments that are coming up first starting the university side, and but now many of these programs are becoming internal to some of the main R&D labs in big companies. So we're at a very interesting transition point where some of us, particularly folks like myself, or typical device engineers, that's how I would describe myself, are being forced in some ways, or coaxed, to learn new tricks in terms of going back and looking at things that I never thought even 5 years back I'd be dealing with. For folks who are not necessarily familiar with Penn State or with the Materials Research Institute, basically I am from electrical engineering, but at Penn State we have four, or right now there's a new institute called Energy. So we have this concept of institutes where Penn State believes that we've got to pull in faculty from different disciplines. So an example of that's MRI. I'm very lucky to be inhabiting this fancy-looking building. We call it the Hilton, the Penn State Hilton on our campus. A big investment by Penn State administration to create a research facility, a state-of-the-art research facility where we have pretty significant nanofabrication capabilities. So all the devices that I will talk to you about, I'll show you, were all built in this facility. We also have a materials characterization lab where we have some of the most advanced electron microscopes, as well as a host of other materials characterization techniques. So I am surrounded. I'm on this side, and on the Materials Research Institute side, and there's the other side is related to life sciences. So Penn State also believes that going forward, we're going to see not only, of course, the information technology industry is going to continue to move along in leaps and bounds, but we are also going to see a lot of convergence between of using electronics or information technology to solve some of the tough problems in life sciences. So the goal was to move some of us faculty members who are interested in this kind of interdisciplinary research to move into a building like this, and I'm surrounded by material scientists, physicists, theorists, all kinds of people, and we're having a good time. So.
Yes, smiling.
So already, last 2-3 days we have been hearing a lot about scaling, so I'm not going to bore you anymore. The main thing I want to point out is that of course, transistors have shrunk quite a bit, and we're at the 22 nanometer node. 14 is entering production next year for some companies. We also heard today the foundry perspective of how they're accelerating their roadmap. So it's action all over, right, from every side. But one of the direct outcome of scaling, at least from some of our perspective, is also the energy efficiency that we have come to enjoy. So of course there's the whole Moore's law economics of it. So here on the y-axis, I'm plotting computation per kilowatt hour. So that's the energy that you're expanding to do a particular computation. And if you plot that, that's also the beauty of log. You're seeing a lot of these exponential increase, and that's about 2x energy efficiency increase every 1.5 years. So computing, of course, getting cheaper. So that's going to probably enable it has from the mainframe to desktop to personal computing, mobility, and then going forward the Internet of Things. So that trend will continue to happen. So from that standpoint, we don't have to worry about the health of our industry. But the other thing is also the energy efficiency, which will also allow you to go for new applications that we have not had before. For example, there's a lot of interest these days of using transit technology for some of these energy-constrained applications like sensor networks or even wearable electronics and so on and so forth. All right, so what do we do in our group? So in my group, we are basically a device group. So we work very closely with materials folks. So we don't do any real materials growth, like for example, molecular beam epitaxy ourselves. So we work with MBA scientists, and we work on a variety of device options. So obviously, our core strength is in semiconductors. I will talk today about 3.5 CMOS devices work that we started off. When I left Intel and started my program here at Penn State. Then I'll talk about 3.5 tau FET. There's a lot of interest now in these sort of devices, and I'll tell you in gory detail, at least my point of view, the good things, the bad things about this, and where we see that there's a potential application. Some quantum devices. Yes, I'm not going to talk too much about that, but we heard the very first day about quantum computation. We were not interested in quantum computation, but we're interested in is, okay, if we continue to scale and we get down to this little island of charge exhibiting this Coulomb blockade characteristic, are there some interesting device architecture or circuit architecture that we can actually build? But that's not what I'm going to talk about today. There is also interest. We had a project related to MEMS integrated with silicon CMOS. So in this particular case, we were looking at very sensitive chip scale magnetic sensor using multiferroic type of device. And that was sort of my entry into the brave world of complex oxide, and that was quite interesting because I had no clue about some of these very, very amazing material properties that you can actually access in complex oxide that are not quite so readily available, at least to my knowledge, in traditional semiconductors. So then I will end. So today I'm going to talk about 3.5 tau FETs, and then we'll talk about a new type of devices that we're very excited about, is taking advantage of what we call this many-body interaction or electron-electron correlation in complex oxide materials. So hopefully we'll get past that without completely boring. Of course, there's some interest, like many groups. We also adapt a little bit with graphene RF electronics. We're still doing some work related to RF mixers, but that project is winding down. All right. So I started off talking about energy efficiency. That with scaling, we sort of took that for granted, and computation got cheaper, but it also got more energy efficient. So we are getting more stuff done, expending less amount of energy. But that's not just given. Okay, we have to work hard for it. And back in the days, what most of us known as the golden days of scaling, the constant field scaling was working before, and for the students, you probably have learned it in your undergraduate textbook stuff. That was quite straightforward. The VDD scaling, and primarily that came from the fact that we had a gate offset, we could scale the gate offset, and we could scale the junctions, increase the body doping, and the so-called Dennard's law of scaling. Professor Mark Lansdorf talked about that, and that worked beautifully. Threshold voltage scale, life was good, basically. But the turn of the century, you can see that, okay, everything is sort of tapering off, and definitely we are not doing constant field scaling. We are not doing constant voltage scaling, we are doing something in between. So basically we are trying to figure out, okay, whatever works in order to make that technology work, right? So, and that started creating some of the problems. And the primary reason that the threshold voltage has stopped scaling is, the number one thing is, first of all, you can't scale because of this subthreshold slope. So if you have to maintain a certain threshold voltage, typically it's around 0.2, 0.3 actually. If you before the days of tri-gate transistors, 0.3 volt. Other than that, your offset leakage current is going to be too high. So now that fixes the VT, which means you need a certain amount of gate overdrive in order to create the on current and deliver performance, particularly for processor applications. So that put a constraint on the amount of VDD, so you need this much of headroom to deal with the on current. So the recent years, voltage scaling has slowed down, and that's a big problem, because once you stop scaling the voltage and you continue to shrink transistors, you not only end up with this problem of overall power of the chip, but also power density issues, because that gives rise to lots of thermal issues that people are quite worried about. Okay, so ideally, we would like to keep going forward and scale voltage again. So, so what prevents voltage scaling? So what prevents voltage scaling? There are quite a few things. First of all, is electrostatics. So we heard today in the morning from Dr. Stadler about the Intel introducing these multi-gate transistors in silicon technology, and the primary driver behind that was that we just can't scale the planar transistors very well anymore. So that option is already looked at. So we would like to. So already the industry has moved from planar to non-planar, and going forward we would like to stick with that architecture and see what else we can do on top of that to continue voltage scaling. So when you think about it that way, then the other thing you can do is, okay, I don't want to give up drive current because I need to deliver a certain performance. So yes, I can play with if I reduce my threshold supply voltage, threshold voltage is constant because of the off-state linkage issues, then the only thing I can do is effective velocity. Okay, so that's what we want to talk and go and look at. Okay, what kind of materials we can pick and how we can design the device around those materials to make sure that we increase the P effective without causing other bad things to our device. So that's the game plan. The other thing, of course, is that let's drop the VTH, and ideally we can drop the VTH to 0 if we can have this abrupt switching transistor, because then you have to get past this switching slope limit of 60 millivolt per decade, and that's why today in the research, at least in our community, device community, you see a lot of work talking about how to make devices with steep switching slope. I'm going to talk about band-to-band transistors, and Saif is going to talk about his negative capacitance devices. All right. And once you exhaust these two, then what do we do? And the question is becoming more relevant, at least for academics like me, because Intel keeps on moving forward, and so does other companies, and they keep taking all these things away. So we have to find new things to work on again that still makes sense. So, so my simple explanation is that, okay, if I have to scale voltage, I have to make the transistor better, but we're already exhausted all the options. So if you can't make the FET any better, then go look for new ways to do computation. So we'll talk a little bit about that, whether that makes sense or not. All right. So let me just skip through. Okay. So just to give you an idea about the kind of stuff that has already happened this turn of the century, and I think it's quite amazing the rate at which we have changed the front-end transistor technology. And you heard about the foundry perspective of how poly-SiON at 28 nanometer and metal high-K is being offered by the foundry. So as a chip designer, you can already access these wonderful technologies. So that to me, the high-K metal gate was a big deal. And I think that there was a reason for some of these technology progression to happen. I'll tell you why. High-K metal gate was our first, when we were working on this thing, and then going back to my Intel days, we learned a lot about work function engineering, actually, that we didn't know. We only had N plus polysilicon and P plus polysilicon, and we had all these band-aid work functions. When we started playing with metal and high-K, of course, we learned a lot about what sets the work function. You would think that it's okay, I can take the vacuum work function of metal, put it down, and that's it. No, it doesn't work like that. There are a lot of interface issues, charge transfer issues, interface dipole issues. There are a lot of fundamental materials issues that you have to actually deal with, defects, to understand what ultimately sets the effective work function, which ultimately sets the threshold voltage. And the industry solved that problem. The industry solved that problem by, first of all, discovering those two magic metals, the N-type and the P-type metal, and then embracing this replacement metal gate technology. And at that time, back in the mid 2000s, that was a pretty big deal to move away from a gate first to a gate-less approach. But I think that experience helped us eventually to go and move to multi-gate, the tri-gate or the FinFET technology, to figure out how to actually target threshold voltage in a fully deployed device. So if you look at textbooks, you would say, no, if you have a fully deployed device, let's take out the doping and select this mid-gap work function metal, and you can move on. Well, that works in textbook. It doesn't quite work that way when it comes to making a real technology out of dry gauge. So we all still use dopants, we still use dual work function metal electrodes, but if we did not have this experience from high-K metal gate, in my opinion at least, we would not have been able to successfully pull off tri-gate technology because of the strict requirements on the threshold voltage targeting. Once we have this, and this is 22 nanometer and 14 nanometer for most people, and then there's a big question mark in our industry right now. And this is where academia, research labs, research consortiums like IMEC, Samatech, as well as some of the R&D labs at IBM, Intel, Global, TSMC soon, and recently we have started talking to Samsung folks. They're all interested in trying to figure out what will be the next big thing. And these kind of non-silicon materials, what are the challenges in order to introduce them in this kind of a high-K metal gate and then this multi-gate setup? Okay, so I'll give you my viewpoints. Then after that, I'll progress to this interband tunnel FETs. And one of the things I want to point out on the left-hand side is also that these kind of materials or transistor architecture make sense only if you're scaling also the supply voltage. And I'll keep coming back and trying to make that point. For example, in my opinion, at least if you're trying to make a tunnel FET and try to overdrive it at 0.8 volt, it's probably not a very good idea to do so. And I'll try to make that point as we go through the experimental work. All right. Beyond that, it's pretty much anybody's wild guess. You can talk about quantum computation to correlated oxides or anything for that matter of fact. But this is where in academia we're having a lot of fun trying to figure out what makes sense beyond these types of devices. Okay. All right. So here we go. So first case that I'll pick up is CMOS, what I call CMOS enhancement. Okay? So you stay with CMOS and try to do whatever you can to make these transistors better, at the same time increasing its energy efficiency. And the main thing that people are talking about is, and we heard that on the very first day, increase the transport in the channel without giving up all the electrostatics and the rest of the other good things. Then there is this CMOS extension. Okay? CMOS extension is sort of like a hook. Okay? So you're still staying with the main CMOS paradigm, and you're trying to introduce these tunnel transistors, which offers switches on based on this band-to-band tunneling mechanism. But when you actually look and try to build these transistors and benchmark these transistors, and then you try to put them in a real circuit environment, then you realize that it's not quite just a drop-in replacement. You have to actually do that due diligence work of understanding the device and the circuit and interaction. So already you're saying that the problem is getting a little bit more complicated. And then going forward, if you're going to go and replace the entire CMOS, well, God help you, because now you're going to go through the entire stack, and we heard about the ecosystem and the EDA tools and the vendors and the validation. I mean, there's a whole bunch of problems. So I think that if we ever, for example, like what we're working on is this correlated electron-based devices harnessing these phase transition. I'll give you an example of a type of system architecture that we are exploring. Now, my personal feeling is that it's probably going to go and address some niche applications. It's not going to go and try to replace some mainstream general purpose. It's just there's too much of a infrastructure already in place for industry to adopt. But that's where mostly when we talk to our industrial partners, they're saying, well, we got this thing sort of under control, or we're looking at this very closely ourselves. You guys go and start exploring this other area. All right. So I'm going to get into the debate of continuum versus atomistic. We have very recently, I've hired actually a postdoc who is starting to do some atomistic simulations, because that's the call of the day. But we have been mostly focusing on continuum simulations, drift diffusion, and as Mark very lucidly explained, that you can capture many of the essential physics of a MOSFET, which is essentially still a MOSFET, if you do the due diligence work of actually calibrating your mobility models, the high field velocity overshoot parameters, and of course you have to do these quantum corrections, because definitely it's a quantized systems and so on and so forth. So the only reason that in a research lab we go through this exercise, or I at least make my students go through the exercise, is so that they know what state-of-the-art is. Because most of the time students don't know what exactly today's 22 nanometer transistor do. And if you don't know that, then anything that you do, especially whether you're working on Fed or not, you're not going to be able to benchmark and really figure out how bad I am or how good I am compared to what already Intel or other people can already do. So here we go. So this is the transfer characteristics of an NMOS, PMOS. We try to fit all the way linear saturation, and most importantly, the subthreshold part. And increasingly, it's becoming very important to model very carefully what we call the near threshold part of the device. And you can see that in order to get this thing all right, not only the transfer parameters have to be carefully calibrated, but you've got to almost take the exact shape of the device. Because that's where you see a lot of the electrostatics is very sensitive to exactly how the cross-section of the fin, this is a silicon fin, look like. Those the rounding of the corners, how it's tapered out, the taper angle, all those things have to, because they are very, very, the junction profile, those things have to be taken into account if you want to do that. So electrostatics, what we have felt, is even more important than many of the transport parameters that we always worry about. So what do we get out of this? What we get out of this is a starting point. That's all we care about. And it gives me a notion of what would be the sort of the injection velocities. We talked about that. Professor Longstrom talked about that. And for my case, I want to see not only how this tri-gate transistor behaves at 0.8 volt VCC, but what happens if I scale. Because now I have this model, calibrate model, I can go and take a look at this, because Intel's paper only talks about 0.8 volt data, and you can actually go and start looking at how would it do at a 0.5 volt, 0.3 volt type of application. This is near threshold or slightly above threshold, and this is now going into what we call subthreshold operation. Okay? So you can see that these are the numbers. So you get about, for NMOS, about somewhere between 0.6 times 10⁻⁷, just to give it a perspective, that's about 60% of the ballistic limit in a silicon transistors, and that has kind of held in that position for a while now, despite all these.
20 years.
20 years almost, yes. That's kind of interesting. But one of the things you see that if you actually underdrive this transistor very quickly, you can see that it's moving further and further away from its ballistic potential. So you can see that this is now operating only at 20% or 40%, depending on the threshold. The other thing I want to point out is, and these are all the things that eventually we'll talk about in the context of 3.5 transistors, is the injection velocity is one thing, and also then the charge, because that velocity times charge gives you the actual current. And the charge, if you were to make these points, today, we are at what? This is 0.8 again, and 0.5. So at 0.5 volt, you're dealing with somewhere between 3 to 5, let's say, times 10 to the 12 per centimeter square. And this is with the state-of-the-art gate dielectric that's out there. Okay? So one of the concerns that sometimes people talk about in 3.5s, you have low mass, you have low density of states, and this is never going to work. Don't even worry about it. That's not quite true. Because even in silicon, where we have plenty of density of states, we have 6 valleys to accommodate all your electrons that you need, we are not overdriving the transistor anymore for a variety of reasons. First is energy efficiency, then there are reliability concerns, and so on and so forth. So once you start operating, if you're taking out today's state-of-the-art silicon transistor, operating them at 6 times 10 to the 12, I think that kind of numbers is very much in the domain of 3.5 devices. So I don't think that's a huge concern, because we are not going to scale gear ups at that aggressive. Okay, so there are different embodiments of how people look at these so-called 3.5 transistors. Just giving it a fancy name, calls it ballistic. But one of the things I will show you that university, what we can do is we can go and start looking at transport a little more carefully. We can build these devices, particularly the long channel ones. In some cases, short-term devices as well. But we can spend more time looking at experimentally the transport parameters and getting these and see whether we're really getting these quasi-ballistic transport or not. Okay. I'm not going to go through this, but by now I think most of you are familiar with how we go from diffusive to this ballistic limit. The Lundstrom and the Notori model. And you can see that we talked about already in the first day of this workshop that the effective velocity has 2 components. One is the diffusive limit that most of us are familiar with, and if you look at all these latest and greatest silicon tri-gate transistor from Intel, they're all still in the in the diffusive limit, and that was that 60% of the ballistic limit. But if you can enhance the mobility, then there's a possibility that this term is not very important, and you can start working your way towards this ballistic limit. All right, let's go. Now, before I go, we get too excited about 3.5 transistor and all these ballistic transistors. The question is which 3.5, right? And there's a lot of history here in terms of people having tried before how to make a 3.5 MOSFET. So whenever you talk to some of my colleagues at IBM, or oh, we were there, we made gallium arsenide MOSFETs, and it doesn't work. It's a completely bad idea. And they have a point, because particularly the high field transport in gallium arsenide, because of all these satellite valleys, you get this valley transfer effect, and that was one of the reasons that they didn't want to pursue gallium arsenide. But that was because they were trying to operate this device in a very high field limit. I think where 3.5 really makes sense is when you're actually dropping all that supply voltage, and you're actually dropping reducing the electric field of operation, and that's when you want to take advantage, because you don't want your carriers to be too hot traveling to the device. That already puts us in a little bit of a different regime. So I don't think any one of us are really trying to even look into this area of gallium arsenide MOSFET anymore. Most of us who are in this area that are working on 3.5 MOSFET or have been are mostly looking at either somewhere in the indium gallium arsenide, somewhere between lattice match to gallium phosphorus 53, 70%, or even trying to push farther and farther out. In fact, you saw from Mark Stettler his simulation example of an indium arsenide FinFET, for example. Of course, you can go further out to indium antimonide, and that becomes a little bit tricky, because then you're compromising quite heavily on the band gap. So then you have all these issues of direct source to drain tunneling, or even band to band tunneling, so on and so forth. But even if you don't go that far and you back off and you're trying to make an in-gas MOSFET, you still have to overcome, which in my opinion is a really, really big problem. And I'm sure the good folks at Intel and other places are working pretty heavily at it, is how to integrate 3.5 with silicon. Okay? Because you have to overcome this very large lattice mismatch. You have to worry about this metamorphic buffer architecture. And the buffer has to be chosen very carefully. So I see a lot of material science, defect engineering, and so on and so forth that needs to go in order to integrate these 3.5 structures on large 300 millimeter silicon platters, right? All right. So this was one of our very early work when I was still a device guy at Intel, and this was 2007 at IEDM when we first showed an in-gas form well that was a 70% that was integrated on these very complicated metamorphic buffer structure on silicon. Most of this is a very complicated structure grown using MBE, but since then people have replicated the structure using MOPP, which is a more manufacturable technique. What was done was, even though this may not be the ultimate metamorphic buffer technology that you want to use for your high volume manufacturing, but it gave us an idea is whether you can even build reasonable MOSFETs or HEMTs, in fact not even MOSFETs, HEMTs on silicon. And then you extract this parameter, the transfer parameter, in this case I'm looking at the electron effective velocity versus some kind of electrostatic parameter. Ideally I would just want to look at ion-I-off. That would be the litmus test. But since these devices are not quite as aggressively scaled in a variety of ways to a straight silicon technology, this was probably the next best thing so-called that you can do in terms of ion and I-off. Okay? So here I'm showing in-gas HEMT on silicon, 70% with different channel thicknesses. So if you reduce the channel thickness, you improve the electrostatics. So transport is never decoupled from electrostatics. So every time you go, and one of the reasons why we're always stuck with 60% of the ballistic limit is because we're always trying to control, for very good reason, the electrostatics of the device. So you get this in-gas, even on HEMT, and you also, for heck of it, we were also at that time working with a company in the UK called Kinetic, who had this indium antimonide growth capability to make these HEMTs, and convince us at that point of time that yes, indeed, you can get all these velocity improvement at matched electrostatics. But here's the caveat. None of these devices had anything to do with the kind of footprint that we were already making the silicon NMOS. So we had this small gate length, that's for sure, but then the contacts were placed miles apart, so all our effective channel lengths were much, much larger than the physical gate length, and that's what, sort of cheating in that sense to match the dibble. But definitely it was the first wave of devices that came out that sort of started a lot of people to get interested in 3.5 for logic applications. Since then, we in our group we were starting to look at whether HEMS are even scalable and single gated HEMS. So these are again very simple Poisson's solution to try to say what kind of, so you can get a single gate, double gate quantum well fed, up and down, inverted quantum well fed, where you can actually change the return to doping and below, bottom barrier doping. Some people today call it this ground plane type of devices. There's a company called Suvolta that's doing this kind. So we looked at many of these architectures in the context of 3.5 devices, because here we can really control doping. If you want to retrograde well, this is probably the best way to do it. And you basically convince yourself that if you were to hit this 7 nanometer or sub 7 nanometer technology node, you have to go with this double gate or multi-gate type of scheme. There is no way around that. Which is not a bad conclusion, because already in the silicon world we have made that transition. So we decided that got us into starting to look at and say things like, okay, if I take a quantum well structure and then I parent them into FENS, okay, how much of that transport that I initially got so excited about, how much of that transport I completely give away? This is that same battle we're facing, is gating back the electrostatics, but then making that compromise on the transport case. And one of the issues is that if you really make a very constricted FEN, and you have all these sidewall scattering, you have these quantum confinement, your subbands are bouncing up and down, creating additional scattering effects, is that going to completely destroy the mobility? So all this great mobility advantage that I'm starting off with is gone. So that's basically moved us in the direction of trying to combine and start looking at 3.5 FinFET to look at this transport effect while maintaining short shell effects. So these are the sort of devices that we can build at Penn State. You can see these an active fin. We decided to put the source and drain completely far out because we were mostly interested in the transfer parameters at that time. So by no means this is a completely scaled device, but it allowed us to make our first 3.5 what I call these quantum well FinFETs. So one of the interesting things that we found right away within the first 6 months of starting this project is this idea that Mark already talked about in the first day, this concept of ballistic mobility. That did not make much sense to us. And so what I'm showing here, these are experimental data for a 40 nanometer wide fin. So it's not a terribly scaled device. It's about 40 nanometer, which is huge in today's dimensions. And we made devices. We were able to extract the drift mobility. The drift mobility in these devices is a function of sheet charge density. And we made 300 nanometer and went down to about 60 nanometer or so in terms of channel length. And when you do that, then you actually start seeing that the mobility is going down. So the question is this a real degradation or artifact of something? So this is the way we extracted the mobility. Turns out that is actually what you would expect. If you have some reasonable transport going on, remember these are still in gas, and the mobilities, in the diffuser limit, you're looking at mobilities in the 6,500 centimeters square per volt second range. And then as you scale this guy, you see that for a given sheet carrier density, the mobility is going down. And that very nicely fits with the fact that you're actually looking at a mean free path that is pretty much anchored to the channel length of the device. Okay, so what does that mean? It means that it actually makes sense that as you inject the carrier from the source, it travels exactly the channel length without much scattering happening, and then it scatters right when it reaches the drain contact. So that roughly makes sense that we are seeing some evidence of these kind of ballistic. Now that doesn't mean that all the carriers, 100% of the carriers are going traveling ballistically, but it seems that give us an idea that maybe yes, at room temperature, you can make these at least 40 nanometer fin devices and just preserve some of these transport properties. But 40 nanometer, obviously, they started to work with a very prominent Asian company that is not happy, obviously, with 40 nanometer, and they want to push us pretty heavily to see whether we can make even smaller fin structures. So I'm a student who has been working very hard in solving these very, really mundane fab issues, but it's a really, really tough problem to etch indium gallium arsenide and make these straight fins, and then figure out how we can make some test structures where we can measure transport parameters. It's actually quite a challenging problem. He has made some progress. We have gone down to now 30 or sub-30 nanometer fins. You can see this fence in a cross-sectional TM. He's getting a lot more vertical sidewall profile than we were getting before, and then we could make these so-called arrays and turn them into gated Hall structure to try to make some gated Hall measurement. The gated Hall measurement, one of the good things is that you can do a pretty reasonable job of getting the conductance and also the carrier density. One of the issues with extracting carrier density in 3.5 devices is because it's kind of hard to interpret some of the CVs, and I'll come to that shortly after. So we've made this, extracted this experimental mobility as a function of the nanowire weight, and you can see that as you go to a planar structure, wider widths, you can get back to this very close to 6,000 centimeter per square per volt second. But as you start getting these, you lose a lot of that mobility that you started off with. We project that at 10 nanometer, we measured up to 30 nanometer, and then we did a projection based on very simple Mattheson's type of rule. And this would be very interesting when we would like to collaborate with theorists on the scattering part. We see about 10 nanometer fin, you're going to get about 3,000, somewhere between 3,000 to 4,000 centimeters square per volt second. Now, obviously, we want to push this thing down to 5 nanometer or 3 nanometer in that range. But one of the questions that I was discussing with Saif, okay, when you're talking about 2D metal caucasionite, you got to actually push these 3.5 devices. You're almost getting that in that range in terms of dimensions, and they're still showing very, very good quality, pretty high mobilities. So something to keep in mind as we talk about this. Now, one of the interesting experiments that we did was we wanted to see, okay, we got this length-dependent mobility. From that we got an idea about that quasi-ballistic transport, but can we really observe ballistic transport at room temperature in these kind of pattern structures? So one test structure that the student came up with, he found from the literature that people had talked about the so-called negative bend resistance measurement. I never heard of this before, but the idea is quite simple. What he talks about, he made basically a Hall cross structure. Instead of a Hall bar, they actually make a Hall cross. You force a current, and then you measure the voltage. So the diffusive limit, the current goes here, and you will actually measure, a positive voltage V2 greater than V1 because it's just a diffusive transport. But what happens is that if you have a ballistic transport across this so-called this intersection, then you can actually see that as you're pushing the electrons, the current is going this way, the electrons are going this way. Just with the forward momentum, there's hardly any scattering, they can actually start accumulating on this other terminal, and that gives rise to these so-called negative bend resistance. And in fact, when he started doing these measurements, then of course what they do is they apply a B field, a magnetic field, to try to divert the electrons back again, and you get back your positive resistance. So you see this negative bend resistance, and when you start seeing that at 300 Kelvin or so, you get an idea about what the mean free path is going to be in a more direct way from these sort of measurements. And we see that in these kind of structures at 300 Kelvin, you can still see this negative bend resistance. Of course, you get a much more prominent variance as you cool this device down, which makes sense because your mean free path is getting longer. So to make a long story short, we did from these transport measurements, we can now go back and try to calibrate our simulators. And one of the things that, okay, we still have to scale these devices down, and how long we'll be able to do that depends on our, of course, our funding. But one of the things we feel at this point of time in terms of projection, this is what I think Mark was talking about. At the early stage, you do things on much more relaxed dimensions, or larger footprint, but then you want to see, as you're scaling these devices, in this particular case, I think the fin width scaling is a big deal, and you try to see that what are the transport, the impact of the transport. So based on that, we project today that once we get to those kind of footprints that we really need in the long term, and the kind of gate lengths that we need, you're going to see somewhere in the range of 2 to 2.5, depending on the way you design this in this structure. And that's still a very healthy 4 to 5x higher injection velocity that you get in today's silicon MOSFET. So that's the kind of drive current improvement that you expect. We're looking at some other variants of these structures in terms of putting stacked quantum wells and so on and so forth that we are fabricating and doing those kind of characterizations. All right, so from the transport side, things look not too bad. But there's another big devil in this business, which is the 3.5 and the high interface. And there's a whole community out there that is just working specifically on this problem. And there has been some remarkable advancement in there. But these are the interfaces that we characterize on our devices, and they are by no means the best interface out there. I think PDA from Purdue University, the Susan Stafford's group at UC Santa Barbara, they've made some remarkable progress, both in terms of getting control, but roughly speaking, we still have issues in terms of controlling the interface between an ALD, atomically layer deposited high-K dielectric, and indium gallium arsenide. And this is where I also think that there could be a lot of collaboration opportunities with the DFT folks and the kind of experimental work that we do in our group. So for example, you're seeing here a CV, and these days people don't talk much about CV because nobody manages CV anymore, but I think it's very important because it gives you a lot of information about this interface. And what you're saying is, I'm not going to go through all the details, basically what you're saying is highlighted in this curve. This is an accumulation mode capacitor, and you see there are two problems. There are some treatments that you can do to make this CV tighten up. This is a frequency dispersion. But as you're trying to deplete of this device, this is an InGas, you see that there is this low frequency response, which is indicative of deep level or what we call the mid-gap states. Okay? So that's going to be bad when you're trying to shut off the device. When you try to turn on the device, so you're going that now your Fermi level is actually moving up closer to the conduction band, you're again seeing a dispersion. Now this has been this I think is very well known from some of the DFT work that people are doing on the origin of these mid-gap defects, but there's a lot of controversy still about the origin of these accumulation mode dispersion. People talk about border traps. Basically these are defects that are extending into the oxide, but it's not clear because when you change the oxide, like you go from hafnium dioxide to zirconium dioxide, you still see these kind of, so changing the dielectric is not changing these kind of accumulation dispersion. So there's something more going on. My hunch is that there is some kind of intermixed layer between the InGas and the high K, and that's the part that we need to carefully look at and find out where the origin of these things. So this is still an open problem. Okay, this is where I think there's a lot of possibility to actually take advantage of DFT. And do very, very close experiments, design experiments together to try to find out where the problem might be. All right. So that gives you an idea about some of the what overall the things are in 3.5 MOSFET. 3.5 PFETs. Okay. In 3.5 PFETs, let's see. This is a weak link. And this has been a weak link for a long time. And all I'm going to tell you is there are some potential candidates. It's not clear whether we will be able to take advantage of any of the 3.5s to make a very competitive PMOS. So people are right now mostly focusing on germanium, right? And there are various reasons that you can actually even strain the germanium. You can actually strain the germanium and improve the performance. But in our work, mostly we have been focusing on the Stanford group is very active in indium gallium antimonide, and we have started looking at this indium antimonide. Okay, I'm going to skip through this thing, and the first work is even to grow these materials in decent quality materials. And one of the things that we do is work with our MD partners to try to design these materials and do these transport measurements to make sure where the effective mass is, because you can play with the compressive strain and so on and so forth. You can do these magnetotransfer measurements, the Shubnikov of the Haas oscillations, extract M star, and make sure that your starting point is right. And of course, you have to deal with the scattering and all the other issues making these devices. So for sake of time, I'm going to now stop and kind of summarize where enhanced CMOS challenges are. I think integrating 3.5 layers of large silicon wafers is still an issue. I give you one example of a HEC, but that is by no means a trivial thing, especially if you have to do it in really tight pitch opening of trenches. Reliable high K dielectric. These are all time t equals 0. Determining the PFET to go with NFET, I think the industry is kind of converging that we'll have a germanium PFET to go with an InGas NFET. And I think it's already late for 10 nanometers, so probably at 7 nanometers is probably the earliest that you can, if we get going, to start to see this. Which means that it's going to come with its own set of design rules that you also have to design this device for. All right. Case number 2. Seamless extension. So this is what already have been talked about before. Mark did a very good job of explaining why we are interested in tunnel FETs. The basic idea is to use this band-to-band tunneling process and use this these band edges to create an energy filter and basically cut off this high energy tail of the direct from the direct distribution of carriers. In the process, you might get this steep slope over certain gate voltage range. So now as you keep applying more and gate voltage and keep opening this tunneling window, you're going to get actually quite a diluted switching slope. So the idea is to find the right set of materials and the right device geometry and engineer the device together, the right doping composition and so on and so forth, to try to see that it actually can beat what I call a subthreshold MOSFET. It is never going to actually compete with, in my opinion, against a super threshold MOSFET, a MOSFET that's already operating in super. So your whole game is you're trying to play within a very, very tight voltage switching space. Okay? All right. So before you go there, and this is again continuum simulation with a very simple WKB type of approximations that you can do for TCAD, and of course later on we try to benchmark these, calibrate these things with experiments, and even compare that with atomistic NEGF NEMO type of simulations. Long story short, basically when you go and try to design a tunnel FET, you see that it's this tunnel barrier is a huge problem. So you try to solve this band-to-band, you try to solve this steep slope, but you physically insert a barrier, and that's a huge problem. Okay, so automatically that pushes you from starting with silicon. Silicon would have been great because we already understand how to make a very high quality dielectric. Now we are moving into InGas. The question is, even in indium gallium arsenide would even be adequate enough for making a tunnel FET. And then you start moving towards even more exotic materials, indium arsenide, and your nightmare just continues to grow because these are exceedingly hard materials just to make a MOSFET, let alone a tunnel FET. Okay, go ahead, Mark.
So in the on state, does MOS electrostatics apply? The charge is C ox Vg minus Vt.
For tunnel FETs?
Yeah.
Not quite. No, I think you're limited eventually by this tunneling barrier.
Oh, but I'm just thinking about the charge. Can I just think about it that the injection velocity is really small because of that tunneling?
Yes.
And the charge is still there, but the velocity is very small.
You cannot populate.
But you're going to populate. That's the problem.
You cannot populate the amount of charge C of Vg will give you.
So what happens is actually if you
That Schottky barrier.
yeah, so actually if you look at it that you have these density states here and you're trying to populate it on both sides, it doesn't do that equally. And this is this fundamental another issue with tunnel FET, that you get these Miller type of enhanced Miller effects. So the rate at which you equilibrate with the source Fermi or the drain Fermi level is different. So that the charge control is a little bit different, and that's one of the things we learned very early on in tunnel FET research. You get these massive overshoots and undershoots when you look at the transients in these devices, and that's exactly the problem. It's an asymmetric device. So anyway, coming back is that you're trying to first of all coming up with the right set of materials that you want to even before making this device. Okay, and well, I mean, this is again in 3.5. You have a lot of flexibility if you're courageous enough, and in this particular case, we decided to not just confine ourselves to the arsenide family. We had some experience working with antimonites before, so we said, okay, let's go and try to work with our MB guys to try to grow these arsenide antimonite type of heterojunctions. Now, this was not a work that started from scratch because the MB community is actually familiar with some of these material systems, completely different application, which is the far infrared photodetector applications. So they actually knew how to make these superlattice structures with arsenides and antimonides mixing. So they were saying, okay, we're up for the challenge. Let's design devices, and we're going to grow it for you guys. And you guys are going to make we're going to make tunnel FETs and try to figure out what's wrong or what's good about these devices. What I'm showing here is again, just looking at the material parameters that was already available. Now, this is another area where DFT could be very useful, trying to understand these exact band lineups. Band lineups is not a very trivial problem. DFT is now doing a very good job. We were seeing in the posters on predicting the band gaps here of the individual elements. But then, as you form these materials, bring them together, it's not quite clear how these lineups are going to be. Okay? So I have two rows here. They're the same material system. One is lattice matched indium phosphide. This is a metamorphic growth. This is going to be a strain growth. So there are definitely some material challenges to be overcome there. And one is the bulk version of it, and the other one is the quantized version of it. Because eventually, you still have to get your electrostatics right. And in fact, getting the electrostatics right in tunnel FET turns out is even more stringent than MOSFET. So you have to scale your body dimensions quite aggressively. Which is becoming almost ridiculous, because in MOSFETs we are talking about 3 nanometer or 4 nanometer type of bodies. My feeling is that at some point we're not going to scale LG anymore. Maybe most probably we're going to park it at 15 nanometer, and then instead of lateral we'll probably start going in the vertical direction. At least the DRAM community has already gone that direction. Okay? So that basically leads me to my second slide, which is tunnel FET challenges. To summarize all these things, okay, you're still looking at a double gate type of architecture. You're looking at a PIN type of a structure. So there's this asymmetry you're talking about between source and drain. And then you've got to get a bunch of things you have to get right on top of all these, which is, so you're going to do some kind of a heterogeneity. So you have a compositional mismatch. Then you have to dope this thing properly. So your doping boundary has to sort of line up with your compositional. If there's a mismatch, then that's an issue. You have to make sure this is a tunnel junction that you're going to gauge on the side. So you have to worry about what the interface states are going to be at that particular edge, right? If you overlap too much the gate with the drain, and in fact Mark was showing that if you try to shut off the device, you get this ambipolar branch, because these are narrow gapped materials. So you probably want to push this back a little bit. In a MOSFET case, that could be a huge problem, especially for silicon MOSFET, a huge or external penalty. But in this particular case, since we will operate them at very low voltages, and the current levels we're dealing with are not too high, maybe we can get away with a little bit of underlap. So there are some real device design issues that you have to go through. The other one that is talked about quite a lot and is very important is the so-called how fast your potential is changing from going from the source into the channel, and that's the electrostatic spreading parameter. This will come back later on when we start talking about, like these days there's a lot of interest in making tunnel FETs in the 2D transition metal dichalcogene. One of the selling points there is, we can get to these very low lambdas that you can't get in traditional semiconductors. Okay, so we have to build this device, right? So we decided to actually go the vertical route, because we thought that there are a few things. Of course, we're going to make our life difficult in some other ways, the law of conservation of trouble, but at least we have some shot at making this device, as Penn say, so we're going to grow this MBE structure with our MBE collaborators. We will design our source, the channel, so the length of the channel will be decided by this thickness, and then we have the drain. We will make these pillars, we'll form our drain contact, we will do this deliberate, timed undercut, and then we're going to do this deposition of metal, which will form my drain contact as well as my gate in some sort of a self-aligned way. Okay, so these are these vertical transistors, the tunneling is happening, this is the tunnel junction here, and you can see the gate that's going to control that particular tunnel injection point. And then you bring out the source. Okay? Interestingly, you can see that in this kind of a device, I also have been able to achieve this drain and gate underlap structure. So I don't have to worry about this ambipolar leakage because I'm not gating that particular junction. Okay? All right. So if you look at that, if you remember that family of devices, yes, you can go with this highly standard system, almost like zero barrier. But in the zero barrier case, it can be, we were not that adventurous, so we decided to go with, okay, let's do a control experiment with small homojunction, indium gallium arsenide, moderate heterojunction, with the barrier height was 0.3 V, and then you go to this very high heterojunction system, which is about quarter EV. So these were the materials that we grew at IQE in Allentown, Pennsylvania. All right. And we actually got fabricated experimental devices. Okay, these are all tunnel FETs. I'm going to first show you the good things, and then I'm going to get to the bad things. The first thing is that they all behaved like almost what we simulated in terms of an experimental output characteristics of a tunnel FET. We also were able to see, so one of the things you're seeing here is applying, typically we only worry about the positive quadrant, 0 to positive VDS, and for different gate voltages, so you're seeing these output characteristics of the transistor. One of the things we saw is output saturation, which is a good thing. So there was a question about whether the electrostatics is going to work out properly for you, and you're going to see this drain side output saturation. What we saw also was quite a bit of enhancement in the drive current as we did this band gap engineering. So you can go from about 60 microamp to 150 to even close to 250 microamp per micron. Okay? So these are some pretty reasonable drive current that you're getting out of a tunnel junction just through the tunneling process. The other interesting thing was if you look at the other side of the VDS, so now we are actually forward biasing the drain to source, you can see that you're seeing this gated tunnel diode characteristics. So this meant that this was indeed a tunnel transistor. There are a lot of work in this field where people think that they have made a tunnel transistor, they claim high drive current, and later on they go back and analyze the device and say, oh, they've made a parasitic MOSFET. And that's what was giving them the high drive current. So one of the things that we always encourage folks to look at if you're doing tunnel transistor, please look at the output characteristics carefully. See that gated tunnel diode is indeed there, and you're seeing this Isaki diode behavior. So that was the first demonstration that we showed enhanced on current using these kind of band gap engineering technique experimentally in the 3-5 tunnel structures. There were a few other things that we learned about the electrostatics of the device as we changed this band lineup. One of the things was the so-called Dibble effect, except we didn't call it Dibble, we call it Divot, because it's a drain-induced barrier thinning problem instead of barrier lowering problem. And you can see that as we went from homojunction to moderate to high heterojunction, you're creating sharper and sharper band bending between the source and the channel. And that's why you're not getting so much interference from the drain electric field. And that's why this Divot effect is getting tighter and tighter. Of course, there's a huge VT shape. So that's another issue, that as you change the materials, you have to go back and redo your entire gate work function engineering to again go back and target the turn-on voltage of this device. All right. Now let's talk about the bad things. Where's the steep KT over Q switching slope? It's quite degraded. Of course, one of the good things is that we are pushing this steep KT, or if you were to the minimum switching slope point to higher and higher drive current, because ultimately that's what we need. But obviously we should be somewhere over here, and instead we're up here. There's a variety of reasons. One of the things is, in order to demonstrate a steep KT over Q, particularly in a short tail, this is still a short tail device, it's 150 nanometer, I think, gate length. You have to hit the right body dimension, you have to hit the right EOT. So you want to make sure that the electrostatic is actually right, because I've seen someone claiming even sub 60 millivolt, and you look at the device and you realize there's no way there can be even sub 60 millivolt per decade for that device, because the electrostatics don't even add up. So that's one thing, but we had bigger problems than that. And I'm going to skip this slide and come back to this problem that has been bothering us for a long time, which is, again, the high K and the 3-5 interface. So what we found was that, of course, if you do a CV, we have this mid-gap DIT. Okay? Now in this case, we went a little bit forward, and once you model the ideal CV, you can, well, of course, you still have to assume some kind of capture cross-section of these traps, but you can get a rough idea of the relative time constant over which these interface states can actually respond, meaning that you're actually looking at the trap dynamics, using the Boltzmann distribution, and at what rate can these traps capture and emit carriers. And that turns out to be in the range of millisecond to about a microsecond. So these are slow traps, and that makes sense because they're away from the band edges. So what we were thinking was, okay, if these gaps have a characteristic response time, can we try to sort of sneak by these traps by doing some kind of a pulse measurement. And now pulse measurement by itself is not very complicated, but now you're trying to do pulse IV measurements in the subthreshold part of the device. So now it's a signal to noise ratio kind of a problem. You're not trying to do pulse measurement at the high on curve. So this is where I guess being at Penn is not a bad idea, because DC is pretty close to us, and we have the NIST folks who immediately said, yeah, we have been working on this. We're always looking for people to come and use our facilities at NIST. And that's what we do. We try to do these fancy measurements. This is not that fancy, but it still requires some custom setup where this is your DUT, and you need a 50 ohm termination so you can send in this high frequency pulses, and then they have this custom amplifier with a large gain stage so that we can actually go and amplify the subthreshold part of the device in the pulse mode. Okay? And when we try to do that, then of course we go through a calibration process. We take a regular, I think we took an SOI MOSFET fabricated by IBM folks, and so the DC and the pulse IV matched up. And then we used our the tunnel feds to look at these pulse IV characteristics and extract the switching slope. What we did find is, as we started going from DC to pulse measurement, this is 600 nanoseconds, 200 nanoseconds, so on and so forth. Yes, you could actually avoid some of these interface states and try to approach, at least in this simulation we were expecting to see, so we had a calibrated simulation to show where we would see the ideal if the DIT was not there, and you could see that we were approaching. We have never seen in our devices anything below sub kT over Q. The best we have seen is close to 60 milli, that to in a pulse IV measurement set. All right. So let's go back, and hopefully I've given you some ideas about some of the difficulties with this device, but then there are some positive things. But it's always good to do a reality check. And the reality check is ultimately what I'm after. Ultimately what I'm after is I want to maximize my on-off ratio over a given gate voltage swing, and that I'm choosing as 0.3 volt. As I will show you, this makes no sense compared to go to higher and higher voltages. 300 millivolt is all I'm going to give myself. I want to maximize this thing, and I'm also going to maximize my drive current. So that's the problem statement. And I already know that I have a pretty good device with which I make money, as we talked about, which is our silicon MOSFET technology. Okay, so I can always target my VT and move on that that voltage window. I can keep moving it, and I can generate this ion. So the question is, if I now put down, based on what I now know about all these tunneling currents, now we go and project these devices. Large EG, high heterojunction, that was the best device that we have got so far in terms of drive current. It's still a hard case to make. Because you're saying that only I go above this white line with this green line, and by the time I do that, this is where I'm breaking even, my drive current is going to be, maximum drive current is going to be about 30 microamp per micron. 30 microamp per micron doesn't sound like a whole lot of drive current to me, even though it's 0.3 volts. So the question is, do you still want to keep working on tunnel feds? Well, at that point of time, you just say that, well, we have not exhausted completely. There's another material that we still can go after, which is this nearly broken. The most extreme type of Bayes lineup. So that's what this year we went after that device. So we said, okay, let's go and try to build a device with only an offset of 40 milli electron volt of barrier, and this is again with NIST. We grew these kind of structures. We put down alumina as some kind of a tunnel barrier. This is one good example where graphene I found was quite interesting. This was more interesting than our graphene RF, like trying to be honest with you. It was a very nice transparent conductor. And we could actually shine light through this thing, excite photocurrent, and see these electron and hole current, and try to get where they cut off, try to get these energy barriers, right? So we did this internal photoemission measurement, and what we found was indeed the structure that was grown, experimentally measured through IPE, is about 20 millielectron volts. So this is as low a barrier as you can get to. And then we proceeded after that to make tunnel feds, the same kind of structures, except in this particular case, we thought that might make a good sense to submit to IDM, something new, which is, this is a vertical transistor, so we used to probe on the drain, the source was here, the gate was on the same plane, so they were all at different planes. Now, ultimately, you don't want to make a device like that, you want to bring them all up to the same level. So we did a planarization scheme and try to bring all these source, drain, and gate pads all at the same plane. And we said, okay, if we have all those things like a normal planar MOSFET, then we can actually go one step forward and do some kind of an RF measurement. Let's try to see the switching behavior, see if these Miller capacities and those kind of effects are really for real or not. Okay? And also we wanted to see that at the limit of scaling, where let's say we need it for 5 nanometer node or not, all these other stuff. So Mark was talking about, yes, we always go after intrinsic device. We spend a lot of time trying to understand our intrinsic device. But now we are at a stage where all this other stuff that is hanging off of from the device is becoming equally important. So we wanted to get an experimental validation of that. I don't have time to go through all the details, but we did get functional devices. We got drain current versus gate voltage, and for a good reason I'm showing it on a linear scale. But remarkably, we saw now peak transconductance of 700 microsiemens per micron. And that's pretty remarkable, given the fact that we are still kind of tunneling through. So you can actually, that bandgap inject did work. We were able to also get measure S parameters at room temperature from this device, and actually could get make this cutoff frequency in the range of 10 gigahertz or so. So that was a gigahertz device range in which this small signal again switching that we could show in tunnel FETs. All right. So, but subthreshold slope is still quite lousy, and that goes back again to how we control interface states and defects and so on, so forth, not only for arsenides, but also for antimonides, which turns out to be a totally different beast when it comes to controlling DIT. Mark talked also about a little bit about how lousy a p-channel tunnel FET is, and he's absolutely right. There's a reason. There are two reasons for that. One is that if you're trying to make a p-channel tunnel FET in the 3.5 system, now your source is, in this particular case, is N+, degenerately doped. And one of the problems of doping N+, the source region is that the Fermi level moves very quickly. It becomes degenerate very quickly because of the low density of states. So once your Fermi level moves very far up, all that band filtering action that you started off with pretty much goes out the window. So now your only option is either engineer the density of state, which is possible with looking at different orientation, but then you have to go back and redo your band simulation, make sure the band wrapping is working properly in the imaginary space, or you have to drop the doping. So if you drop the doping, then you're going to get a longer lambda. If you get the longer lambda, that kills your electric field. Your electric field gets weaker. So yes, this is a very, very hard problem trying to design this thing. But anyway, we went ahead and tried to go after a gallium antimonide, indium arsenide. We did gallium antimonide, indium arsenide p-channel tunnel FET as well. But what we found was bigger problems. If in-gas and high K is a bad problem, when you go to actually moving the Fermi level, particularly the valence band side on a gallium antimonide, it's even a bigger problem, and we see a lot of interface state issues with those devices. So that's one of the areas we're working on how to get a better interface state density. If you look at the output characteristics of this p-channel tunnel FET, yeah, we were getting some reasonable current. Actually, we went up to even 80 microamp per micron. But you can see that it's an asymmetric device, but because of the weak gate coupling to the channel, you don't see this output saturation. So you can see that these are not at all a well-tempered device at all. In the remaining 5 or 6 minutes, I'm going to give you a little bit. I'm going to talk about the last part, which is the correlated electron. But before I go there, one of the things that we have also done, and I won't have time to go through, is in the tunnel FET work, is to go from devices to circuits. And that seems to be a very urgent theme these days, especially as we are looking at these emerging devices. So the way we do that in our group is, of course, we do a lot of these TCAT. We do actual device fabrication, so we go through that calibration process. We also work with the Purdue folks on trying to calibrate or cross-check the TCAT simulation with the atomistic simulation. We generate a lookup table. We make sure we capture both the DC and the transients. You can see these overshoot effects because of these asymmetric charge control issues. And then we try to put this in a circuit simulator. So we have this working. We're actually going to the next stage where we are even developing some library level issues with tunnel FETs and doing a full full processor simulation with this is with Professor Raghunathan's group at Purdue. So, the most important take-home message from these devices is that yes, even if tunnel FET works, let's say, it's going to work in a range when so this is energy versus delay, and you can do that for inverter. This is a delay for a 32-bit adder. It only works when you drop your supply voltage below 0.5 volt or so. Okay, so which means that you can also see as you drop the supply voltage, you're also increasing your delay. Okay, so this is not a device where you want to clock things very fast. And normally we would not even consider devices like that. But when you start talking to the architecture community, they said, oh, wait a second, this may not be such a bad idea given the problems that we are facing today, which is this whole idea of dark silicon. So we are in this era of multi-core. And one of the biggest problems today is that, let's say, people say multi-core solves all the problems, but that's not quite true. There are many cases where it happens that serial applications, you have to run serial applications, and at that point they have a fixed power budget. They can only turn on only so many cores out of all the available courses because cores that are available. So they run into this issue. In this particular case, you can see the 4 cores are turned on, but the rest are all basically shut off. So it's like a load shedding that's very popular in the country I come from, and because of this for all these power limitations. So this dark silicon is becoming a big issue for these guys. Okay? So now they're saying that if you give me a heterogeneous technology where I can have some CMOS core and some tunnel FET core, yes, now I'm going to rethink my architecture differently, the way I allocate power, the way I do my thread allocation, the way I do my runtime, compiler time optimization is going to be very different. And this is an area where we're saying, at least in my experience for the first time, we're going from devices to compact models, to libraries, and even talking to an architect. So those are the kind of things. When you come back and try to look at more mundane circuit issues, you already run into problems because, for example, SRAM, this is one of those circuits that is very widely used. You realize that in tunnel FET case, I might have made some mistake, because it's an asymmetric device, the way you orient this tunnel FET is set. So unlike CMOS transistor where source and drain are interchangeable, in tunnel FET you cannot do that. And that creates issues when you're trying to look at optimized read-write operation in tunnel FET-based SRAMs. And so we looked at some of those types of issues. So what is the take-home message in TFETs? I think the on-current issue that was initially flagged as one of the biggest problems, at least in my opinion, that may not be the big issue. The big issue right now is the steep slope. But then again, you're dealing with some very difficult family of materials. P-channel, big problem. There are no good demonstrations. It would be great to start looking at these germanium tin type of applications, but that also is not a very easy material to grow. So I think the P-channel conflict is a big, big, big question mark. And without a P-channel, we're not going to be able to make a complementary. We have device models that show some advantage where we might be, where system guys might be able to take advantage of it. But my feeling is that the 3-5 MOSFETs obviously has to happen first. The tunnel FET is a little even more complicated. And if we run into problems here, then most likely we're never going to see 3-5 tunnel FETs. So the real problem to solve first is 3-5 MOSFET, but it seems like that's going on in 4-man. All right, I think Saif is going to talk about 2D chalcogenide, but let me just point out to the fact this is the first time that I actually hired someone to start doing atomic simulation in my group, and that's the need of the hour because we're kind of getting out of compound semiconductor-based tunnel FETs, and now we're venturing into the brave new world of 2D materials and trying to see whether making tunnel FETs or any other MOSFETs even makes sense in these type of devices. And so we're looking at not only this number of layers effect, strain effects, and so on and so forth, like many other groups. We're also kind of interested, this is a new thing that my postdoc just brought to my attention, that which goes back to revisiting graphene. Because basically what we found, at least from our standpoint, is that the PIN, if you make PIN tunnel FETs out of 2D chalcogenide, it didn't show very high drive current, despite the fact that the splitting lengths are extremely small. But the band structure didn't look very helpful in terms of getting enough on current. So we're going back to graphene. The biggest problem with graphene is you don't have a band gap. So the question is, can we start thinking of bilayers to break this inversion symmetry, open the gap, and go and revisit graphene again. But the biggest problem there, I see at least, is a lack of ability to make realistic junctions. And unless we solve the junctions issues, there's no way we can even attempt to make these devices. Okay, so we can do a lot of simulations, but that's about it. All right, the last thing, I don't know how much time we have, like 2 minutes maybe? 2 minutes and wrap up? 10? Okay. So in 10 minutes, I'm going to give you this is an area we are quite excited about, and because we've never seen this kind of, or never had a chance to play with these kind of materials before, and this is the area of complex oxide where we move away from the so-called, what we call the S and the P electron, and start dealing with the d electrons. So one of the things about these d orbital electrons is there's a strong electron-electron interaction. And that gives rise to what we know in condensed matter as this many-body effects. Of course, the superconducting community, they have looked at these things in great detail. But we are interested in whether it makes sense to look for switching devices, let's say FETs, or maybe something else beyond that. So one of the ideas is the so-called Mott-Hubbard insulator, and for folks who are familiar with it, basically the idea is that these are, we know band insulators and we know band conductors, right? So you can solve your DFT and get this, whether there's a band gap or not. But these materials, the band gap opens only when, just because of the Coulomb interaction, the very strong on-site Coulomb interaction between these electrons basically sets up a situation where the electrons cannot really hop from one side to another. Okay? So this, it's just an energy cost. It's just too high for electron to hop from one side to another because of the strong repulsion. So they end up sitting where they are, roughly speaking, and you open what we call as the Mott-Hubbard band gap. Okay? Now the theory is, at least, we can argue that if I add a few more electrons or take a few more electrons out or add holes, then I can upset this delicate balance, and then I collapse this gap, and suddenly I go from a Mott insulator to a conductor. Okay? So that's kind of interesting, at least from a device standpoint, that hey, I can induce this phase transition and abruptly turn on. Well, it's not quite clear whether it should be an abrupt process or not, but there's a potential to go from to induce a phase transition. And people have looked at it called the MOT-FET before at IBM, and I think they're revisiting that in terms of the F electron, the material systems. But so we started off with, of course, you need a material. In this particular case, we found that vanadium dioxide, very popular material. People have been looking at it for 50 years, and there's still a lot of controversy in terms of exactly what this transport is and what fundamentally causes this phase switching. So this is a very well-known curve in vanadium dioxide, completely experimental. Rho, resistivity as a function of temperature. So you can see that there's an insulating phase, and then as you increase the temperature somewhere around room temperature, and this can change depending on strain and dimensionality and so on and so forth. It abruptly switches, goes to a metallic state, and then you come back, and there's a bit of this hysteretic behavior. Okay? So this is good in terms of temperature, and you might invoke Mott physics to explain this data. But you also can invoke what we call Farrell's type of transition, where there's a strong interaction between electrons and lattice that can also explain some of these resistivity change. So we said that, okay, we will try to, at least when you write a proposal, you said, okay, I'm going to incorporate this in a device and try to make these devices. Okay. So, okay, when you start with a new material, the first thing, at least what we do, is again go back and redo the transport and try to get familiar with this material and the nuances of this material. So what we found is that the physics that I talked about before, but it's clearly not as straightforward as just the Mott physics. It's not that you exceed a Mott criteria, you collapse the band gap, and you come back again. There is definitely what we find is a structural transition that is also happening. And this is one of the unsolved problems in VO2, and people go back and forth. What happens first? Some people think there's a correlation effect that kicks in before, which in turn then the electrons interact with the lattice and creates a structural change. And the jury is still out. And I'll show you some of our own data that still points, I think, to some of this electron correlation effect. So you go from this monoclinic insulator phase to a rutile phase. You see this dimerization of this vanadium atoms that happens. But anyway, in the insulating phase, it's not quite an insulator. You actually see some what we call this polar unhopping. And with the way we know that is from all these temperature-dependent transport measurements. One of the things we did was we sent a student down to Argonne National Lab, the advanced photon source, and they were able to do this in situ, which I thought was spatially resolved X-ray, nano X-ray, and electrical characterization. So we are able to actually switch this device by passing electric current. So we can go from a low resistance state, the high resistance to the low resistance. You can see this switching pulse, and we can actually track with an X-ray exactly what the structural evolution of this film is. And one of the things we find is there is this, the entire material doesn't turn on at the same time. There are some local filaments that start developing, and you go through this structural phase transition before it goes from insulator to metal. We got, but one of the things that we were encouraged by is that yes, you can actually apply a VDS. So this is the VO2 channel, source and drain, just a two-terminal device. You can apply a VDS, and you can actually see the insulating phase, and boom, it goes to the metallic phase. You clamp the current, you don't burn out the device, and then you can come back, and you can see that there is some kind of scaling that happens with respect to channel length, with respect to channel width. Bottom line is, and more importantly, as we change the temperature, we also saw that there are some very interesting trends in terms of where exactly this switching from insulator to metal happens. That turns out always that it always switches at a constant resistivity. Now, if you assume a certain mobility from an independent Hall measurement, we always find that there's a critical carrier density, 3 times 10 to the power 19 per centimeter cube, at which always this switching happens, which again starts leading credence to the theory that hey, maybe not so different from the Mott criteria in this particular material. So it's not quite as simple as that you're passing a current, you're heating up the device. It has nothing to do with that. There's always this critical carrier density over at which the switching happens. I'm going to skip this thing and encouraged by those results, then we said, okay, but it's still not quite, in a two-terminal measurement, you can never separate out Joule heating versus a pure electronic trigger transition. You ultimately need a three-terminal device. And a lot of folks are at least trying to make this device working, and we made an attempt, and what we found was that yes, actually you can apply a gate voltage, you can apply a different drain voltage, so this is our sort of transfer characteristic measurement, and you can actually see this is the resistive phase, and boom, after a certain point we were able to turn on the device, clamp it. And this one we did it for different VGS, so the gate field and the drain field is actually helping you to turn this device on and off. But obviously it's the range is pretty lousy, but you could actually get some three-terminal characteristics. This again starts. Go ahead.
What happens at the underlap region?
The underlap region? No, this is an overlap. The gate is overlap with the source.
Can the gate actually turn on your VO2 in that region? Because the offset thickness is much larger.
The offset thickness is, so you can see, VO2 and offset is almost the same. This is a 3 nanometer or 4 nanometer VO2, and about another 3 nanometer.
So if you go to your schematic, right underneath the gate,
yes,
you have a thin offset, right? But in the overlap regions, right here, between source and gate, right?
Yes.
Here your oxide is much thicker.
No, this is the same oxide thickness, right? ALD. So we put down source on the VO2, source drain, and then we do the gate is overlap. So the gate actually extends out over here. So it's not an underlap device. It is an overlap device. We can talk about, okay? So we actually see that you can actually switch this conductance with a gate electric field. The problem is that when we go one way, and we actually go from the insulating to the metallic state, we cannot come back. Because now, if you apply a gate field and you're trying to deplete of this device, you're trying to deplete of a metallic. And we try to scale down. Our VO2 channel thicknesses are already in the 3 to 4 nanometer range. But that still seems that we don't have enough gate field penetration capability. So we tried some different type of experiment. We said, okay, the other thing is that even if you succeed in turning off this device, when you go and look at what is the on-state resistance, and if you compare with what we can today do with gallium nitride, or there are lots of electrons in this system, or silicon even, it doesn't look like that you want to make a VO2 MOSFET by itself. It's never going to be as competitive as your regular MOSFET, even if you get this steep switching. Okay.
So we said there must be other ways to start looking at these devices. And one of the things, in fact, very similar to what Saif even proposed before, this is what I call a resistance analog of how to stabilize a negative differential resistance domain in a phase transition device, and try to see whether we can do something useful with this negative differential resistance. Typically, let me just go through this thing. You have current versus electric field. This is VO2. And forget this resistor. This is a stabilizing resistor that's going to ultimately apply this negative feedback. You apply the electric field, you get to this so-called, let's say, Mott criteria, and then some kind of a positive feedback mechanism kicks in, and you go from insulator to metal. And then if you come back, there's always this hysteresis loop, and now we understand, why, exactly quantitatively what's this difference is. Then you come back, and eventually you cannot sustain this carrier concentration, and you go back into the insulating state. Then you can go back and forth with this hysteretic type of a behavior. But if you just add this simple trick of a resistor in series with this device, then what happens is you can actually, under certain conditions, and you can work those conditions out on simple feedback theory, that you can actually start uncovering this so-called negative resistance. This is a metastable state that you don't normally see in this strategic switching, which is exactly equal, the slope of this is exactly equal to -1/Rs of this stabilizing resistor, and you can start seeing that. One of the interesting things we found after that was, okay, we have an NDR, so what? But then, let's go through this story just for a few minutes. You apply an electric field, and then you see that because of these feedback resistance, the field actually starts dropping across the actual VO2, because there's more current flowing there. And when the field drops, then it cannot sustain that metallic phase that it needs. So then again, it goes back with the temperature. You're holding the temperature constant. So you're trying to bring this device back into its insulating state. Then again, it comes back. Then the field develops again. And then it goes back again to the metallic state. So you can actually create a situation if you work out the math properly, that you can actually make even a sustained oscillator that will just keep on going back and forth between this metastable insulating and metallic phases. And that's exactly what we did. We were able to show that under this particular set of conditions, that you can actually make these are not sinusoidal oscillators, they're called relaxation oscillators, where you go through this IMT phase, then you relax, and then the next cycle begins. Okay, so these are the power spectral density, which is not too bad actually, given if you benchmark them against the spin torque oscillators, for example, which is very popular these days. This looks like a very healthy power output from these devices.
How stable is that?
It's pretty stable. You can set it up, and it just keeps on going. In terms of endurance, number of cycles, you can go for it. Yes, absolutely.
Well, there's a lot of strain.
There is a lot of strain. Yes, so I think that this electron lattice interaction is probably okay if it's happening at a unit cell level, where these vanadium atoms are dimerizing and undimerizing. I don't see that would necessarily create a huge amount. But of course, you have to go and do this detailed endurance test. At least what we see is that since we're not driving a whole lot of current with these devices, they're very stable. We have done even scaling studies that I'm not showing here that shows exactly how this oscillation frequency is scaling even with the size of the device. So one oscillator is interesting, but we're really after is whether we can show coupling between the oscillators. And recently we have done measurements. We can do this charge coupling through a high pass filter, and that's the kind of oscillation dynamics that we're actually working with folks at Georgia Tech. Where we showed that there's one oscillator uncoupled, the second oscillator, we deliberately set up these frequency differences, and then we, by changing this coupling capacitance, we can get them to couple and synchronize. And right now we are working on the math to try to see what kind of phase relation. The nonlinear dynamic problem is very complicated. It's already complicated for two, and then you actually start scaling it up. But it's a lot of fun working on these set of devices. What would couple oscillators do? There is a lot of interest these days on things called associative process. This is my last slide, or second last slide, where people are talking about that if I have an array of oscillators with different levels of coupling, weak coupling and strong coupling, then you can actually excite your input pattern. You can excite a set of oscillators, and then you can feed in these template images to set up to another set of oscillators, and depending on how quickly they sync up, you can actually do certain kind of pattern recognition type of application. So what is the concluding thoughts? The concluding thoughts is, I always tell when I talk to my students or postdocs or anybody giving a talk, that I always try to answer, are we always working on the, quote unquote, the right problem that this community cares about? In our case, this particular talk, at the end of the day, it comes down to improving performance for what? If we can achieve that with whatever devices we are proposing, I think that would be an important contribution. Plausible solution that I was trying to talk about today is these quasi-ballistic devices. We have some evidence, but we also have a lot of problems to still solve going forward. Steep slope devices, yes, there are certain things we can engineer out, but then there are some very tough interface-related issues that we still have to deal with. And then very new areas of correlated electrode devices. I'm pretty sure there are a lot of new physics that will come out from these dynamics of these oscillatory devices. I'm just giving you one example. And then, of course, once you have this proposed solution, you have to perform the research, and that involves a host of this thing. It's not just simulation, or it's not just fabrication and characterization. It's everything from modeling, simulation, whether it's continuum, atomistic, DFT, whatever is needed to try to understand transport, device design, electrostatics, and of course fabrication characterization. One of the important things I always stress about is we have to find a way to benchmark our results. We cannot just throw a result out and say, oh, this is the best device. Because there is already an entrenched technology. There are already very innovative ways where we can solve current problems. So somehow speed, scalability, energy efficiency, reliability is another big area. And I think I'm seeing more and more interaction between a device person, materials person, but we're also trying to go upstream and start talking to circuit and system designers as well. And last but not the least is the knowledge transfer. I don't want to keep things just in my lab. I feel good about it. We have to engage with the industry practitioners often and most likely early, because we get a lot of good feedback when we talk to the folks out in the industry. They tell us, okay, this is something we're already doing internally. Don't worry about it. We'll take care of it. You go and focus on other stuff. Give seminars just like this and publish with enough details so that other people can actually pick up their work and validate and even see whether we're right or wrong. And send students out, whether it's collaborating with another lab or internship at these companies, where I think that gives a very healthy atmosphere of trying to create a very collaborative culture. And I think these are the sort of things that we generally pursue in our group to try to create a program. So with that, I'll just thank our sponsors and mostly the team that works pretty hard in the lab building the devices, making the devices, simulating the devices. Thank you for your attention.
Questions?
I have one here.
Hi, I have a question about your oscillators.
Yes.
So a few questions actually. So how big are they and how scalable are they, both in terms of frequency and in terms of power?
Yeah.
And
So the oscillator that I showed you were probably less than even a megahertz. They're about 5 micron in size. Okay. So the way we set up this oscillator is, if it's a 5 micron device, that's the resistance of the DUT. So I have to choose my series resistance also proportionally to that. If I scale my device, then I'm going to scale that series resistor, the negative feedback resistor, and that way I can actually scale the device. We have gone up to 1 megahertz. That's with a 2 micron type of devices. But one of the things we want to do is to try to push this, how fast we can go, because ultimately we want to go to gigahertz or so at least, to make this useful. Now the only other thing I can tell you is that we did some impedance spectroscopy, not for oscillators, but in general on the transport. And we see this evolution as we heat up this device and we go from the insulator to metal. And from that impedance spectroscopy, if you look at the small signal circuit, we think that we can get down to about a nanosecond, or maybe slightly less than a nanosecond. So it's not going to be a tenth of gigahertz like the STOs, but it might have a fighting chance to get to that gigahertz.
and any potential advantage in the long term in terms of per cycle power dissipation?
I think when I look at the input power, what we are feeding in and what we are getting out of the oscillator, that's not too bad. In fact, we just blow the STO guys out of the water, to be honest with you. But however, this is a relaxation oscillator. This is not a.
This is not an LC or
This
LC
is
line.
not an. So we haven't done, and I think in the expedition project, this is one of our goals is actually to do this power performance, the whole analysis. So I don't have a clear answer, but right now one of the things that we're worried about is the phase noise. The phase noise is very high. You can see that from the power spectral density. So, but on the other hand, this is a charge-based coupling. So so we're gonna go head to head with the STO guys.
So of course you're thinking of using these oscillators as power, as essentially microwave kind of power supply devices, right?
Well,
microwave energy supply devices. Suppose I gave you a different question. I didn't care about how much power came out of it. Okay. In fact, I also don't care too much about phase noise.
Mm-hmm.
I want to reduce. I just want it to oscillate, and I want to reduce the power consumption as much as possible per cycle.
Then I think to just the scale. I think it will come down to the scalability of the device, right? That's it. How small we can make.
Thank you.
Other questions?
Actually, we talked about the steep slope device. Actually, one question always in my mind is what's the target subslope swing we should go for?
What is the
target subslope swing we should go for? I think it's not the smaller the better. So
Oh, okay. What is the optimal? Okay, so I think that you can always use subthreshold CMOS, right? You can always target a VT, get to low IF, eventually eliminated by gate leakage or junction leakage, but you can always get that. I think we're not going to do tunnel fits. We have to get certain drive current out of these devices as a minimum requirement. My feeling is that if we can get 30 average subthreshold, don't worry about the minimum, 30 to 35 millivolt per decade over maybe 2 or 2.5 orders of magnitude, and we get a reasonable drive current that we're going after, I'll call that quite an accomplishment. So 30 millivolt per decade, average over 2.5 orders of magnitude of drive current change. That's it. But it has to turn on and off within that 300 millivolts, 350 millivolt of swing.
Okay, I think we should get a coffee break. And so we take break for 10 minutes and come back at 3:50.